Hi friends, welcome back to our series of sessions on energy conservation aspects. Today we shall be discussing about HVAC and refrigeration. The heating, ventilation and air conditioning, as we popularly call it as HVAC, and refrigeration system transfer heat energy from one atmosphere to the other. One of them is closed environment, while the other is the open atmosphere of the earth. HVAC includes the bidirectional flow of heat in the sense that when Earth's atmosphere temperature is too low, then the requirements of a closed atmosphere are to be maintained. Heat is injected into the closed atmosphere. Refrigeration, on the other hand, has a unidirectional flow of heat. It always extracts heat from the closed atmosphere with the help of a low boiling point refrigerant and dispels it into the open atmosphere of the Earth. According to the thermodynamic laws, heat cannot flow from cold object to hot object unless external work is done. The external work is done by the equipment used in HVAC or refrigeration using electricity as the energy source. There are several heat transfer loops in the refrigeration system as described. As we see in the figure, thermal energy moves from the left to the right as it extracted from the space and expelled to the outdoors to the 5 loops of heat transfer. We're saying compressor is here, condenser, expansion valve, evaporator, the 4 very important elements. In the leftmost loop, indoor air is driven by the supply air fan through the cooling coil, where it transfers its heat to chilled water. The cool air then cools the building space. Chilled water loop. Driven by the chilled water loop pump, water returns from the cooling coil to the chiller's evaporator to be recooled. Using a phase change refrigerant, the chiller's compressor pumps heat from the chilled water to the condenser water. In the condenser water loop, water absorbs heat from the chiller's condenser and the condenser water pump sends it to the cooling tower. The cooling tower fan drives air across an open flow of the hot condenser water, transferring the heat to the outdoors. So that's exactly what happens in the cycle of the refrigeration system. We are seeing here, all these are the heat transfer loops. Supply air fan, this is the chilled water pump, this is the compressor, this is the condenser pump, and then cooling tower fan. So we have air here in the beginning and air in the end. In between we have water and then getting cooled with the refrigerant getting evaporated inside the evaporator and giving up the heat in the condenser. It is taking the heat in the evaporator, giving in the condenser. So through condenser we are giving away the water to the heat to the water, and which in turn in the cooling tower it is being given off to the air. That's exactly what happens in the refrigeration system. Depending on applications, there are several options, combinations which are available for use. As we see, air conditioning, split air conditioners, fan coil units in a large system. Let's understand the refrigeration system. A small capacity modular units of direct expansion type, similar to domestic refrigerators, small capacity refrigeration units. Centralized chilled water plants with chilled water as a secondary coolant for temperature range cover 50 degrees centigrade typically. They can also be used for ice bank formation. Brine plants which use brines as lower temperature secondary coolant for typically sub-zero temperature applications, which come as modular unit capacities as well as large centralized plants. The plant capacities up to 50 ton are usually considered as small capacity, 50 to 250 ton as medium capacity, and over 250 ton as large capacity units. A large industry may have a bank of such units, often with common chilled water pumps, condenser pumps, cooling towers as an off-site utility. If we understand the capacity measurement of the refrigeration system, the capacity of household refrigerators is measured in liters of volume of the enclosed chamber, which is to be cooled. The capacity of the air conditioning system is measured in terms of ton-hour refrigeration. The term 1 TR means the rate at which heat is extracted. 1 ton signifies that amount of heat required to melt 1 ton of ice in 24 hours. This can be derived as 1 ton is equal to 907 kg. Please note, 1 kg means 1 metric ton. The latent heat of ice, if you see, it is 80 kilocalories per kg. Hence, the rate of extraction of heat is equivalent to 1 ton, or will be 907 into 80 divided by 24, which gives 3024 kilocalories per hour. And 3024 kilo divided by 0.252 gives it in British thermal units as 12,000 BTU per hour. Since this is an ideal conversion assuming no losses, the operating efficiency criteria of any HVAC or refrigeration system will be judged by kilowatt per ton hour. So effectively, it will be 3.52 kilowatt. 1 ton refrigeration is equal to 3.52 kilowatt. That's exactly what we need to understand. So let's understand the types of refrigeration system. The two principal types of refrigeration plants found in industry include vapor compression refrigeration and vapor absorption refrigeration. Vapor compression refrigeration uses mechanical energy as the driving force of refrigeration, whereas vapor absorption refrigeration uses thermal energy as the driving force of refrigeration. Let's understand the vapor compression refrigeration system. We have the condenser, evaporator, compressor, expansion valve, and condenser here. Heat flows naturally from a hotter to colder body. In refrigeration system, the opposite must occur. That is, heat flows from a colder to hotter body. This is achieved by using a substance called a refrigerant, which absorbs heat and hence boils or evaporates at a low pressure to form a gas. This gas is then compressed to a high pressure in compressors, such as that it transfers the heat it has gained to ambient air or water and turns back into the liquid, that is, gets condensed into a liquid. In this way, heat is absorbed or removed from a low temperature source and transferred to a high temperature source. The refrigeration cycle can be broken down into the following stages, where we have from 1 to 2, we are seeing here. Low pressure liquid refrigerant in the evaporator absorbs heat from its surroundings, usually air or water or some other process liquid. During this process, it changes its state from a liquid to gas, and at the evaporator, exit is slightly superheated. Then if you see from 2 to 3, the superheated vapor enters the compressor where its pressure is raised. There will also be a big increase in temperature because a proportion of the energy into the compression process is transferred to the refrigerant. Then from 3 to 4, the high pressure superheated gas passes from the compressor into the condenser. The initial part of the cooling process, that is 3 to 3A, desuperheats the gas before it is then turned back into the liquid 3A to 3B. The cooling for this process is usually achieved by using air or water. A further reduction in temperature happens in the pipework and liquid receiver 3B to 4A, so that the refrigerant liquid is subcooled as it enters the expansion device. Then the last cycle from 4 to 1, the high pressure subcooled liquid passes through the expansion device, which both reduces its pressure and controls the flow into the evaporator. It can be seen from the entire diagram that condenser has to be capable of rejecting the combined heat inputs of the evaporator and the compressor. That is from 1 to 2 plus 2 to 3. This has to be the same as 3 to 4. Therefore, there is no heat loss or gain through the expansion device. To see the alternate refrigerant for vapor compression systems, the use of chlorofluorocarbons is now beginning to be phased out due to their damaging impact on the protective ozone layer present in the troposphere around the Earth. The Montreal Protocol of 1987 and the subsequent Copenhagen Agreement of 1992 mandated a reduction in the production of ozone-depleting CFCs, refrigerants, in a phased manner, with an eventual stop to all production by the 1996. In response to the refrigeration industry has developed two alternative refrigerants based on hydrochlorofluorocarbon HCFCs, another based on hydrofluorocarbon HFCs. HCFCs have 2 to 10% ozone depletion potential as compared to CFCs and also have an atmospheric lifetime between 2 to 25 years as compared to 100 or more years of CFCs. However, even HCFCs are mandated to be phased out by very soon, and only chlorine-free zero zone depletion HFCs would be acceptable. Until now, only the HFC-based refrigerant HFC 134A has been developed. HCFCs are comparatively simpler to produce, and 3 refrigerants 22, 123 and 124 have been developed. The use of HFCs and HCFCs results in slightly lower efficiencies as compared to CFCs, but this may change with increasing efforts being made to replace CFCs. Then if you understand the absorption refrigeration, we have the alternate refrigerants for vapor compression cycle. Then we have the absorption refrigeration. The absorption chiller is a machine which produces chilled water by using heat such as steam, hot water, gas, oil, etc. The chilled water is produced by the principle that a liquid, which is a refrigerant, which evaporates at low temperature, absorbs heat from the surroundings when it evaporates. Pure water is used as refrigerant, and lithium bromide solution is used as absorbent. Let's see the absorption refrigeration concept. Through this table, we have the evaporator, that is the refrigerant evaporates at around 40 degrees centigrade under a high vacuum condition of 754 mm of Hg pressure in the evaporator. Chilled water goes through the heat exchanger tubes in the evaporator and transfers heat to the evaporated refrigerant. The evaporated refrigerant in the vapor form turns into liquid again, while the latent heat from this vaporization process cools the chilled water from 12 degrees centigrade to 7 degrees centigrade. The chilled water is then used for cooling purposes. Then we have the absorber. In order to keep evaporating, the refrigerant vapor must be discharged from the evaporator, and the refrigerant in the form of water must be supplied. The refrigerant vapor is absorbed into lithium bromide solution, which is convenient to absorb the refrigerant vapor in the absorber. The heat generated in the absorption process is continuously removed from the system by cooling water. The absorption also maintains the vacuum inside the evaporator. Then we have the high pressure generated. As lithium bromide solution is diluted, the ability to absorb the refrigeration vapor reduces. In order to keep the absorption process going, the diluted lithium bromide solution must be concentrated again. An absorption chiller is provided with a solution concentration system called a generator. Heating media such as steam, hot water, gas, or oil perform the function of concentrating solutions. The concentrated solution is returned to the absorber to absorb refrigerant vapor once again. Then coming to the condenser, to complete the refrigeration cycle and thereby ensuring refrigeration takes place continuously, the following 2 functions are required. Number 1, to concentrate and liquefy the evaporated refrigerant vapor, which is generated in the high pressure generator. To supply the condensed water to the evaporator as refrigerant in the form of water, and for those 2 functions, a condenser is installed in the entire system. Absorption refrigeration system that use lithium bromide and water as a refrigerant have a coefficient of performance in the range of 0.65 to 0.70 and can provide a chilled water at 6.7 degrees centigrade with a cooling water temperature of 30 degrees centigrade. Systems capable of providing chilled water at 30 degrees centigrade are also available. Ammonia-based systems operate at about atmospheric pressures and capable of low temperature operation, that is less than 0 degrees centigrade. Absorption machines are available with capacities in the range of 10 to 1500 tons. Although the initial cost of an absorption system is higher than that of a compression system, operational costs are much lower if waste heat is used. Then let's see the common refrigerants and their properties. A variety of refrigerants are used in vapor compression systems. The choice of fluid is determined largely by the cooling temperature required. Commonly used refrigerants are in the family of CFCs, chlorinated fluorocarbons, and also called freons, R11, R12, R21, R22, R502, R7 ammonia. And these are all the different, their boiling points, freezing point, vapor pressures, vapor volume, and the total heat. Enthalpy is nothing but total heat in kilojoules per kg when it is in the liquid form, and kilojoules per kg in terms of 385 when it is in the vapor. Because from liquid to vapor, the enthalpy, we have what is called as the latent heat that is available in the vapor, whereas in liquid, only the sensible heat will be available. Then this is when you see the performance of refrigerants at 15 degrees centigrade evaporator temperature, the 30 degrees centigrade condenser temperature, the coefficient of performance, we can see the refrigerant R11, R12, R22, R502, R717, then evaporating pressure is so much, condensing pressure is so much, the pressure ratio is so much, vapor enthalpy and COP, Carnot coefficient of performance is 5.03 for R11, whereas it is only 4.37, the lesser for R502. This is exactly what it is shown. So if you see the selection of a suitable system, a clear understanding of the cooling load to be met is the first and most important part of designing or selecting the components of a refrigeration system. Important factors to be considered in quantifying the load are the equal cooling load, heat leaks or cool leaks, and the internal heat sources from all heat generation equipment. Consideration should also be given to the process changes and or changes in ambient conditions that might affect the load in the future. Reducing the load, like through better insulation, maintaining a cooling temperature as practical as possible, is the first step towards minimizing electrical power required to meet refrigerant needs. With a quantitative understanding of the required temperatures and maximum, minimum, and average expecting cooling demands, selection of the appropriate refrigeration system, whether it is a single stage, multi-stage, or economized, is designed. Now, this table basically gives the different parameters for vapor compression chillers and vapor absorption chillers with lithium bromide. For reciprocating, this is the refrigeration temperature range. For centrifugal, +7 to 0 degrees centigrade. For screw compressors, +7 to 25 degrees centigrade. For vapor absorption, for all effects, it is above 60 degrees centigrade. That's the refrigeration temperature that will be maintained. Energy input is electricity for vapor compression system, because we have to drive the compressor, whereas for vapor absorption system, we don't require much of mechanical power, electrical power, because it's all because of the combination of heat and cool between hot water and oil. Then we have the air conditioning temperatures, which may range from for reciprocating 0.7 to 0.9 kilowatt per ton hour, and whereas from the 5,000 kilocalories per ton hour, because its electricity is given in kilowatt, its heat given in kilocalories per ton of refrigerant. Then the refrigerants are for vapor compression, we have all these. And then for vapor absorption, we have only pure water, pure water, pure water. So we are not using any refrigerants when it comes to the vapor absorption chillers. That's the main objective. And absorbent not required for compression-based systems. And for vapor absorption, we have the water lithium bromide solution as the water absorbent. Then air conditioning temperature range 1 to 150 we have, and for the main disadvantage of vapor absorption chiller is we can't have more than 30 or maximum 50 ton of refrigeration. Sub-zero temperatures is preferable for vapor temperature, but not for vapor compression. Typical coefficient of performance at part load up to 50% reduces for vapor compression cycles and improves for screw compressors. Marginal improvement at part loads for this. So if you see the performance assessment of refrigeration plants, the cooling effect produced is quantified as tons of refrigerant, as we have just seen TR. 1 ton refrigeration is 3024 kilocalories per hour of heat rejected. The refrigeration TR is assessed as Q multiplied, the total Q is the mass flow rate of coolant, CP is the coolant specific heat in kilocalorie per kg, Ti is the inlet temperature of coolant to evaporator in degrees centigrade, T0 is the outlet temperature of coolant from evaporator in degrees centigrade. And the above TR is also called chiller tonnage. This is the performance assessment what we do. 1 ton hour is calculated based on this Q into Cp into Ti minus T0 by 3024. So if you see the theoretical coefficient of performance, Carnot COP, which we standard call, a standard measure of refrigeration efficiency of an ideal refrigeration system, which depends on two key systems temperatures, namely the evaporator temperature, TE, and the condenser temperature, TC, with COP being given as TE divided by TC minus TE, that is cooling effect in kilowatt by power input to compressor in kilowatt, where the cooling effect is the difference in enthalpy across the evaporator and expressed as kilowatt. The effect of evaporating and condenser temperatures are given in this table. So here we have on x-axis, we have the temperature leaving chilled water in degrees centigrade, and on y-axis we have increase in COP. See, for absorption refrigerators, we have the low increase in COP with the temperature leaving chilled water, where it slightly increases from reciprocating from centrifugal to screw compressors. So screw compressors are considered to be the most efficient when it comes to in terms of evaporating temperatures. So similarly, the reduction in condensing temperatures, the more condenser temperatures, if we reduce, the more efficiency we have. Similarly, for centrifugal, absorption, reciprocating, and for screw compressors, percentage increase in CVP is more for screw compressors than for others. Then let's see the factors affecting performance and energy efficiency in refrigeration plants. The various factors which affect the performance and energy efficiency of the refrigerant. Number one is the design of heat exchangers. There is a tendency of the process group to operate with high safety margins, which influences the compressor suction pressure or evaporator set point. For instance, a process cooling temperature of 15 degrees centigrade would need chilled water at a lower temperature, but the range can vary from 6 degrees centigrade to 10 degrees centigrade. At 10 degrees centigrade chilled water temperature, the refrigerant side temperature has to be lower, say by 5 degrees centigrade to plus 5 degrees centigrade. The refrigerant temperature again sets the corresponding suction pressure of the refrigerant, which decides the inlet duty conditions for the work of compression of the refrigerant compressor. Having an optimum driving force, that is nothing but temperature difference, can thus help to achieve the highest possible suction pressure at the compressor, thereby leading to less energy requirement. This requires proper sizing of heat transfer areas of process heat exchangers and evaporators, as well as rationalizing the temperature requirement to the highest possible value. So at a 1 degree centigrade rise in evaporator temperature can help save almost 3% on power consumption. That's the thing. So if you see the evaporator effect of variation in evaporator temperature in compressor power consumption, given at a condenser temperature of 40 degrees centigrade, towards rationalizing heat transfer areas, the heat transfer coefficient on the refrigerant side can be considered a range from 1400 to 2800 watts per meter square degrees centigrade. So this is the evaporator degrees centigrade, you will see. Then 5%, 5 degrees centigrade in evaporator temperature, refrigeration capacity is 67 point, specific power consumption is 0.81. So as the temperature goes down, there is an increase in kilowatt per ton of refrigerant at a given condenser temperature. Then if you see the role of compressors, condensing temperatures and corresponding condensing pressures, because condensers in a refrigerant plant are critical equipment that influence the tonnage, refrigeration capacity, and the power consumption demands. Given a refrigerant, the condensing temperature and corresponding condenser pressure depend on the heat transfer area provided, the effectiveness of heat exchange, and the type of cooling chosen. A lower condensing temperature or pressure in the best combinations would mean that the compressor has to work between a lower pressure differential, as the discharge pressure is fixed by the design and performance of the condenser. The choices of condensers in practice range from air-cooled with water spray, and heat exchanger cooled. Generously sized shell and tube heat exchangers as condensers with good cooling tower operations help to operate with low discharge pressure values, and the TR capacity of the refrigeration plant also improves. Then with the same refrigerant R22, the discharge pressure of 15 kg force per square centimeter with a water-cooled shell and tube condenser and 20 kg per centimeter square with an air-cooled condenser indicate the kind of additional work of compression duty and almost 30% additional energy consumption required by the plant. One of the best options at the design stage would be to select generously sized, that is 0.65 meter square per ton of refrigerant and above shell and tube condensers with water cooling as against cheaper alternatives like air-cooled condensers or water spray atmospheric condenser units. Then if you see the effect of condenser temperature on refrigeration plant energy requirements, this is the condenser temperature from 26.7 to 40. Refrigeration capacity reduces from 31.5 to 20. Then 1.17 to 1. The specific power consumption, kilowatt hour per ton of refrigeration improves from 1.17 to 1.41, whereas an increase in kilowatt per ton of refrigeration from 8.5 to 20.5. That's the thing we need to know. So then we have maintenance of heat exchanger surfaces. The second most important factor in energy conservation. After ensuring procurement, effective maintenance holds the key to optimizing power consumption. Heat transfer can also be improved by ensuring proper separation of the lubricating oil and refrigerant, timely defrosting of coils, and increasing the velocity of secondary coolant, that is air and water, etc. However, increased velocity results in larger pressure drops in the distribution system and higher power consumption in pumps and fans. Therefore, careful analysis is required to determine the most effective and efficient option. Fouled condenser tubes force the compressor to work harder to attain a desired capacity. For example, a 0.8 mm scale buildup on condenser tubes can increase energy consumption by as much as 35%. Similarly, a fouled evaporators result in increased power consumption. Equally important is proper selection, sizing, and maintenance of cooling towers. A reduction of 0.55 degrees centigrade temperature in water returning from the cooling tower reduces the compressor power consumption by 3%, as we see in the figure. The power consumption is also lower than that for systems typically available in India. The next one is the multi-stage compressors for staging for efficiency. Efficient compressor operation requires that the compression ratio must be kept to low to reduce discharge pressure and temperature. For low temperature applications involving high compression ratios and for wide temperature requirements, it is preferable and often economical to employ multi-stage reciprocating machines or centrifugal or screw compressors. Multi-stage compressors are of two types, compound and cascade. They are applicable to all types of compressors. With reciprocating or rotary compressors, two-stage compressors are preferable for low temperatures from 20 to 58 degrees centigrade and with centrifugal machines for temperatures around 43 degrees centigrade. In multi-stage operation, a first-stage compressor sized to meet cooling load feeds into the suction of a second-stage compressor after intercooling of the gas. That's what we need to understand. The next one is the matching capacity to system load. During part load operation, the evaporator temperature rises and condenser temperature falls, effectively increasing the COP. But at the same time, deviation from the design operation point and the fact that mechanical losses form a greater proportion of the total power negate the effect of improved coefficient of performance, resulting in improved part load efficiency. Therefore, consideration of part load operation is important because most refrigerant applications have varying loads. The load may vary due to variations in temperature and process cooling needs. Matching refrigeration capacity to the load is difficult exercise, requiring knowledge of compressor performance and variations in ambient conditions and a detailed knowledge of the cooling load. That is also equally important. Then we have the capacity control and energy efficiency. The capacity of compressors is controlled in a number of ways. Capacity control of reciprocating compressors through cylinder unloading results in incremental modulation as against continuous capacity modulation of centrifugal through vane control and screw compressors through sliding vanes. Therefore, temperature controls requires a careful system design. Usually, when using reciprocating compressors in applications with widely varying loads, it is desirable to control the compressor by monitoring the return water, the temperature rather than the temperature of the water leaving the chiller. This prevents excessive on-off cycling or unnecessary loading and unloading of the compressor. Capacity regulation is also very important through speed control. However, when employing speed control for reciprocating compressors, it should be ensured that the lubrication system is not affected. In the case of centrifugal compressors, it is usually desirable to restrict speed control to about 50% of the capacity to prevent surging. Below 50%, vane control or hot gas bypass can be used for capacity modulation. The efficiency of screw compressors operating at part load is generally higher than either centrifugal compressors or reciprocating compressors, which may make them attractive in situations where part load operation is common. Screw compressor performance can be optimized by changing the volume ratio. In some cases, this may result in higher full load efficiencies as compared to reciprocating and centrifugal compressors. Then we have the multi-level refrigeration for plant needs. The selection of refrigerant system also depends on the range of temperatures required for the plant. For diverse applications requiring a wide range of temperatures, it is generally more economical to provide several packaged units instead of one large central plant. Despite the advantages of packaged units, central plants generally have lower power consumption since at reduced loads, power consumption can reduce significantly due to the large condenser and evaporator surfaces. Many industries use a bank of compressors at a central location to meet the load. Usually, chillers feed into a common header from which branch lines are taken to different locations in the plant. In such situations, operation at part load requires extreme care. For efficient operation, the cooling load and the load on each chiller must be monitored closely. It's more efficient to operate a single chiller at full load than to operate two chillers on part load. The distribution system also should be designed in such a way that individual chillers can feed all branch lines. Isolation valves must be provided to ensure that chilled water does not flow through chillers not in operation. Individual compressors should be loaded to their full capacity before operating the second compressor. In some cases, it is economical to provide a separate smaller capacity chiller which can be operated on an on-off control to make peak demands, with larger chillers meeting the base load. Then we have the chilled water storage. Depending on the nature of load, it is economical to provide a chilled water storage facility with water. Depending on this, the storage facility can be filled to meet the process requirement so that chillers need not be efficiently used or operated continuously. The additional cost of cooling to a lower temperature may offset benefits. The solutions are case specific. Then we have system design features. In overall plant design, adoption of good practices improves energy efficiency significantly. Some areas for consideration are designing of cooling towers with FRP fiber reinforced plastic impellers and film fills, PVC drift eliminators, etc. Use of softened water for condensers in place of raw water. Use of economic insulation thickness in cold lines. Heat exchangers considering cost of heat gains and adopting practices like infrared thermography for monitoring applicable especially in large chemical, fertilizer and process industries. Adoption of energy efficient heat recovery devices like air-to-air heat exchangers to pre-cool the fresh air by indirect heat exchange, control of relative humidity through indirect heat exchange rather than use of direct heaters and chilling. And finally, adopting of variable air volume systems, adoption of sun film application for heat reflection, optimizing lighting loads in the air-conditioned areas, optimizing a number of air changes in the air conditioning areas are a few other examples which need to be considered in the system design features. So that's all for today. I hope this video clearly gives the holistic approach of the heating, ventilation, and air conditioning system, including the in-depth analysis of refrigeration. Thank you very much.